Chapter 5, Concurrency Fundamentals, Threads, Executors, and Completable Future. Chapter 5, Concurrency Fundamentals, Threads, Executors, and Completable Future introduces the core concurrency tools Java developers need before moving deeper into thread-safe state, virtual threads, reactive systems, and advanced performance tuning. The important shift is that Java concurrency is no longer only about creating threads or choosing a thread pool size. Modern Java asks a more architectural question. What kind of work are we coordinating, and which concurrency model fits that work best? For many years, Java concurrency was built around platform threads. A thread was essentially a wrapper around an operating system thread. That model is powerful, but expensive. Each platform thread consumes meaningful memory for its stack, is scheduled by the operating system, and carries non-trivial context switching cost. Because of that, enterprise Java applications traditionally used thread pools through executor service. Instead of creating unlimited threads, applications reused a bounded number of platform threads to protect the process and the operating system. That traditional executor model still matters. Platform thread pools remain useful for CPU-bound work, native blocking work, legacy libraries, and cases where the amount of parallel work must be tightly controlled. If a workload is doing encryption, compression, image processing, large calculations, or other CPU-heavy tasks, adding more threads than available cores usually does not help. It often makes performance worse. For CPU-bound work, the goal is not massive concurrency. The goal is efficient parallelism. The picture changes for I/O-bound work. Many back-end systems spend most of their time waiting for databases, downstream services, message brokers, object storage, identity providers, and external APIs. In the old platform thread model, each blocked request occupied a costly operating system thread. This meant that applications could appear saturated even when the CPU was mostly idle. Threads were not busy computing. They were waiting. Project Loom and virtual threads change that model. As described in the supplied update material, modern Java now separates platform threads from virtual threads. Platform threads remain the operating system-backed threads. Virtual threads are lightweight JVM-managed threads that are mounted onto a smaller set of carrier platform threads. When a virtual thread performs supported blocking I/O, the JVM can park the virtual thread, save its continuation, free the carrier thread, and later resume the virtual thread when the operation is ready. This is the crucial idea. The code can look blocking, but the underlying carrier thread is not wasted in the same way. Are so important for modern backend Java. They let engineers return to a clear thread per request style for many I/O-heavy systems. Instead of splitting logic across complex callback chains or reactive pipelines just to avoid blocking, developers can often write ordinary sequential code and still get high concurrency. That improves readability, debugging, profiling, and maintainability. Executors still exist in this world, but the way we use them changes. With platform threads, pooling exists because threads are expensive. With virtual threads, pooling the virtual threads themselves is usually the wrong idea. A virtual thread per task executor creates a fresh virtual thread for each task. That sounds wasteful from the old mental model, but it is exactly the point. Virtual threads are cheap enough that reuse is not the main concern. The new concern is not how do we limit thread creation, but how do we protect the resources behind the work? That distinction matters. If a service receives 50,000 concurrent requests, virtual threads may allow the application to represent that concurrency cleanly. But that does not mean the database, payment gateway, fraud service, or partner API can handle 50,000 simultaneous calls. In the Loom era, thread pools are no longer the right primary backpressure mechanism for I/O-bound work. Explicit controls such as semaphores, rate limiters, timeouts, bulkheads, and connection pool limits become more important. The update material makes this point clearly. Virtual threads should not be pooled for reuse. Downstream pressure should be controlled separately. Completable Future is a Nuth concurrency toolbox. It was introduced before virtual threads and became a common way to compose asynchronous work without blocking platform threads. It is useful when tasks must be combined, transformed, raced, retried, or handled as a dependency graph. Methods such as then apply, then compose, then combine, exceptionally, all of, and any of allow developers to express asynchronous pipelines. But completable future has trade-offs. It can make complex flows harder to read. Logic becomes fragmented across lambdas. Debugging can be harder because execution moves between threads. Stack traces may lose the clean shape of the original business operation. Thread pool selection also becomes part of the design. If blocking work is accidentally scheduled on the wrong executor, it can starve unrelated tasks. Virtual threads do not make completable future obsolete. They reduce the number of situations where completable future is needed only to avoid blocking. Completable future is still useful for true asynchronous composition. Virtual threads are often better when the code is naturally sequential but blocked on I/O. A senior engineer should not frame this as old versus new. The better framing is, use completable future when composition is the core problem, use virtual threads when readable, blocking style I/O concurrency is the core problem. Structured concurrency also becomes important here, although this chapter only introduces the idea. The problem with launching independent tasks is lifecycle control. If one task fails, should the others continue? If a request is canceled, who cancels the child tasks? If 3 downstream calls are started together, how do we join them safely and propagate failure clearly? Structured concurrency treats related tasks as one unit of work. That makes cancellation, failure handling, and observability easier to reason about. There are still risks. Virtual threads are not magic performance dust. They do not make CPU-bound work faster. They do not remove the need for thread-safe data. They do not protect downstream systems automatically. They also require awareness of edge cases, such as pinning. The supplied update highlights that Java 24 changed monitor behavior through JEP 491, so virtual threads are no longer pinned simply because they block while using ordinary monitors, but pinning can still occur around native calls or foreign function interactions. Monitoring with Java Flight Recorder remains useful for spotting rare JDK virtual thread pinned events. The senior takeaway is that concurrency is not about matching the abstraction to the workload. Platform thread pools are still relevant for CPU-bound and legacy work. Virtual threads are the modern default candidate for high concurrency I/O-bound backend services. Completable future remains useful for asynchronous composition. Structured concurrency helps manage related concurrent tasks as a coherent lifecycle. Good Java concurrency design is deliberate. It keeps code readable, protects shared state, limits pressure on downstream systems, propagates cancellation, exposes useful metrics, and remains debuggable in production. Modern Java gives us better tools than before, but the engineering responsibility is the same. Choose the simplest model that gives the system the throughput, safety, and clarity it actually needs.